Hey everybody, this is my video walkthrough for Dreamth, the project that I did for the Handmade Network Lisp Jam. So this is just going to be kind of a casual walkthrough where I try to cover what the project is, the high level of how it works, give you a little bit of an intro to doing programming in Dreams, and stuff like that. So to start off with, I'm just going to run a quick little demo program that I have here. This is running a simple arithmetic expression. It's doing oh good, it fell apart already. This happens. It's a bit of an amusing bug with the program. Most programming languages don't have gravity turned on, but this is doing the expression 1 plus, in parentheses, 2 times 5. I'll probably put that math expression down at the bottom of the screen so that it's easier to see. This structure that you're seeing is basically how you would see it in a typical Lisp, so I'll have that version of it up on screen too. Anyway, I can click on a list node here, one of these purple things, in order to evaluate it and run it like a function. That kicks all this stuff off, and it starts moving things around, spitting things out over there, and eventually comes up with 11, which is the right answer. That's 1 plus 2 times 5. So it's doing the right thing. And we can collect garbage, and we could run it again and stuff, but I'm going to try to get right into the meat of the explanation here. So this is obviously not what you would consider a traditional Lisp. This was an idea I had for the jam kind of right away. I thought of the name right away as well and was like, man, with a name like Dreamth, how can I not do that for the jam? So it's an interesting one, and in order to explain how everything works, I want to start by giving you a bit of an introduction to programming in Dreams. So I'm going to hop out of this and hop back to another version of this project where I have some demo and educational stuff already prepared right over here. So let's start by giving you a brief introduction to the programming or logic in Dreams. So basically everything is done with these wires and what they call microchips and gadgets. So a microchip here is just a little panel for code and gadgets to live on, although they can absolutely live outside. It doesn't really affect the logic. What I have here is some light bulbs that I pulled in from the Dreamiverse, which is their little community of creations, and I have them rigged up so that when I turn these switches on, the light bulbs will turn on. So this lets you see the gist of how this works. You can see that when I turn the switch on, this wire is now powered, and it is sending a signal to this microchip, which turns on the bulb. This one at the bottom is using the calculator, which is multiplying the value on this wire by, in this case, 0.5. And you can see that this light bulb is on basically half brightness, and I can adjust this by changing the value slider here. So the first thing that I want to point out is that all of these wires, every single wire in Dreams, is basically just a number, a floating point number. In this case, we're seeing that a 1 is coming into the A. When it's off, it's a 0. When it's on, it's a 1. Those are the numbers that the switch produces. The value slider down here is doing an arbitrary number, and you can see that as I adjust this, we can preview that result on the calculator node here in real time. So that's the very basics. If we slide over to here, we'll see that there can be more interesting kinds of wires as well. So this little gadget here is called a combiner. It takes multiple values and combines them down into a single, what they call a fat wire, which is basically just a bundle of wires that has some meaning, and the various meanings, the types, are available here. There's a variety of them for different things in Dreams. The one that I have picked for this example is the simple 3 numbers type. So this makes a fat wire of 3 numbers. I can actually wire this into another calculator, and now, when I turn these on, I can actually multiply all of them at once, because the 2, 3, and 4 number types in Dreams actually play nice with math operators and sort of behave like vectors, if you're familiar with that. In general, the calculator just does the same thing to every component of the fat wire. The splitter here simply pulls the fat wire apart into individual things again, so I can pass it off to the light bulbs. The next gadget that I want to show over here is the Selector. Many gadgets in Dreams logic actually have their own internal state, and this is a very simple example of that. So I have to actually start playing time. You can see that I've now pressed the right stick and time is playing up here. This allows state to change over time. So what happens now is, as I turn this switch on and off, it's wired into the move to next output node on this selector gadget. And when I do this, it advances the selector to the next option, and this will just continue cycling around. I can also use these switches that are directly wired into ports A and B to switch directly to that state whenever I want, without having to go to the next states in between. This gadget will get used a lot later on, as you'll see. There's also some other simple things that I wanted to make sure I covered. There's Boolean Logic. We have ands and ors here, so you can see that that's doing exactly what you would expect it to do. There's also this thing here. This is a signal manipulator, and it's used for a variety of things, but primarily in this case, it's used to turn a constant signal into a pulse. You'll see that when I turn the switch on, the light bulb blinks very quickly and then turns off again. A pulse in Dreams is basically a signal that's only on for one tick of their simulation. And it's useful when you want to make sure that you have kind of an instantaneous input. I have to use this every so often, and if you see this, you'll at least know what that's there for. And finally, we get to what's probably the most interesting part of this whole Intro to Dreams logic demo. These are what are called wireless transmitters and wireless receivers. So what these allow you to do is to send data back and forth without actually explicitly connecting wires between things. And this is kind of the foundation of the whole project, because as you've seen, you can kind of just snap things together and they start communicating. So the way that this works is the wireless receiver has a volume around it in which it will actually receive wireless signals. And then this wireless transmitter will actually connect to that receiver whenever it's in range. So right now, I have this switch on and wired into the transmitter. You can see that the transmitter is black, which means that it has a value. And when I drag this into the receiver's range, the receiver turns black to indicate that it is now outputting a value, and the blue light bulb turns on. So this is a very simple form of wireless transmission. I'll also mention that the wireless receiver can have a variety of different shapes and sizes for its zone. I could, adjust the range, the radius that way. There's also an option for scene, which will make it basically pick up wireless signals from anywhere in the scene and not even do any volume checks. I use that in a few places. The really interesting and potentially surprising thing about wireless transmitters, though, is that they're actually kind of the same thing. They're symmetrical in some sense. It's just that one happens to have the volume on it. What I mean by this is that you can actually send values back from a receiver to a transmitter the same way that you can send from a transmitter to a receiver. And you can see that here because I have this red switch, which is wired into the input of the wireless receiver. And when I do this, it actually sends a signal back to the wireless transmitter, which is wired into this light bulb. So every transmitter-receiver pair can basically communicate bidirectionally. The communication can go both ways, and this is extremely important because it's basically what allows me to send and receive messages, in a sense, between all the different objects in the Dreamth runtime. Basically what I want to do now is go into more detail about how running a Dreamth program actually works. We need to have a good idea of what's actually happening when it runs so that the code will actually make any sense. So let's start with these here. These are const cells. Now you may be familiar with the concept of a const cell in the sort of abstract sense. Basically, everything in Lisp is made of linked lists. And these nodes are nodes in the linked list. Basically, each one of them has a value, which goes on this top little knob here, and then a next pointer in some sense, but basically a reference to the next node. So that's represented by this thing off to the right. Now, normally in Lisp, you would have parentheses in order to denote this stuff. And if I snap together an example list, then I can put up on screen what the corresponding Lisp syntax would typically look like. I think that'll be instructional because it'll help you understand exactly how this system works. So this list here is simply the list containing the values 1, 2, 3, and then nothing at the end. So this is kind of the typical form of a list in Lisp. You have a const cell with a value and a next thing, a value and a next thing, a value and then nil for its next thing, which indicates the end of the list. Now, in some sense, if I were to snap this on here, this is now still a valid Lisp data structure, but this is where the dot syntax is typically introduced so that you can make some distinction for this special case where instead of having a nil to indicate the end of the list kind of just ends in something else. There's specialized syntax in Lisp for this, but really in Dreams we don't need anything like that. We are already seeing the underlying structure of the list right here, so we don't really need any of that stuff. I'm going to throw that 4 away. So this is the basic structure of const cells. It's worth noting also that in order to make more complex expressions possible to lay out in this system, I actually needed a way to keep lists from sort of overlapping and occupying the same physical space, as you're seeing they're starting to do here. My solution for that was actually that you can just rotate linked list nodes, and this does not change the structure, it just changes where they are. And that's important because physical proximity is actually how most of this system works. So this is really the same list as before, I was just able to rotate nodes. Now, the next most important feature of a Lisp probably is the ability to actually call functions or, do anything. So that's where I have this little math function here. So this can do 4 different arithmetic operations. It can do addition, subtraction, multiplication, division. In theory, this system could perform any function, but all I had time to implement was this one bit of arithmetic. Unfortunately, that means it can't do anything super Lispy, but hey, what do you do? It was a jam project. So it's worth noting that this little, I'll call it the arithmetic primitive or the math primitive, it's got these little things floating above it, and you can see them sort of like rotating with it in a funny way. So those are part of the execution, and you've seen in the demo that those are flying all over the place when it's running. Those 3 things belong to this math primitive here, and they are effectively analogous to different things that you might have in like a typical Lisp implementation. This bottom one here is a linked list walker. This one is something that's following a pointer and calling effectively one type of function, and this is following a pointer and calling a different type of function. So we'll see what they do in more detail in a second after I uncollapse my program here. Of course, the final building block is a number, and the number is just a simple block that has a value, and by pressing the up and down buttons on the controller you can adjust it so that you can actually make these expressions happen. So we need to actually evaluate this in order to get a sense of what is going on. So I'm going to turn this back into kind of a simpler expression so that we can kind of see what's going on. I'm going to snap together basically 1 plus 2 plus 3. So we'll grab another cell over here, turn that into a 3, that into a 2. We're going to grab another plus here. And I'm going to actually pull this out of the way just to make my job easier in video editing. You're really seeing the whole process here. But basically, I'm going to run this and pay attention to what these different lights are doing as the execution happens. And I'll probably slow this down in the video and cut into it so that you can actually see in more detail what's going on. All right. I was sort of talking over that, and I figure you'll probably want to see that again in more detail, so let me just run that one more time. So, if you're watching carefully, you'll notice that this gold one here runs to the 1, then runs to this const cell, and then waits there for a while. And every time the gold one runs to a node, the blue one is close behind and goes to the car position, the value position of each const cell. The blue thing is the evaler, the evaluator, and its job is to go to each of the values and ask it to evaluate itself to something that can actually be used in an expression. Now, many things in Lisp sort of just evaluate to themselves. A function evaluates to itself. A number evaluates to itself. Those are both things that can be just used as values. The main difference here is that a const cell, when you ask it to evaluate to a value, it actually calls itself as, it calls the list that it makes up as a function. So that means that calling the blue evaler actually triggers this plus to start going, which starts it running down its own list and so on. The green thing is a value grabber, as I call it, and its job is basically just to get values from things after they're done. And you can see that very clearly in that after this plus finishes evaluating and its result, a 5, is dropped over here, this green value grabber runs all the way over there to grab that value for this plus so that it can finish up the expression. And let's watch that one more time. And indeed it works. So this is the general model of evaluation in here, and now basically we get to look at the code and actually see how some of this is implemented. And it's going to get a little bit crazy, but that's how it's going to be. So here we are back in the other scene where we can see all the code. And back here, we have a lot of code. So let's flip on over here and take a look at all the code that belongs to the three primitives that we just looked at. The const cell, the math primitive thingy, and a number. So you can see there's a lot going on here. But basically, we have one microchip for each of the things I just described. We have the const cell itself, it's called primitive plus, but the math primitive, the list walker, the evaler, the value grabber, and the number itself. So, before I get into the nitty-gritty of this, and we get lost in the weeds talking about a bunch of different things, the way to think about this project and the way that it works is basically as each of these things as a little state machine sending messages to other state machines. That's the best way I've found to think about it, and it's the model that makes the most sense in this system. Dreams is, in some sense, very object-oriented. You have this logic that's snapped onto objects, and you have wires that form explicit communications between things. Or you have wireless transmitters that sort of implicitly do it based on other conditions. But ultimately, none of them are happening, well, they're happening concurrently in some sense, which effectively turns this into a CSP-like problem, or generally just kind of a concurrent problem, and these things need to be sequenced. And they're sequenced by explicitly sending signals back and forth over wires in order to tell each other what step to move on to. Now, keeping that framework in mind, let's dive in and start looking at the const cell itself. So, there's a lot going on here. The thing you'll probably notice the most is there are a lot of wireless transmitters and wireless receivers. Each of them is on a different channel, so to speak. By using names, you can sort of make different channels for wireless transmitters and receivers so that they don't overlap with each other. There's a lot to look at. We have this one here called identity, which is a signal that basically just reports who am I to anything in the area that cares. We have pos here, which is just the object's position. We have, because this is a const cell, car and CDR identity, in other words, like the value and next pointer identities, because we happen to have things there that can pick that up. We've got receivers for apply, which is the thing that we tell to a primitive or a function to say, hey, here is a list of arguments, please do your thing. We have this here for eval, which is basically telling the car position to evaluate itself, all sorts of stuff. And I'll break some of these down, not all of them, because there's too much here to go through in this video. But one fundamental thing to know is that we do down here have an ID. So every object in this system has a unique ID. And we have this thing here that I call an ID broker. Oops, hold on. which I call an ID broker, which is just a very simple thing that is incrementing a global variable every time something asks for an ID, and it is reporting that ID to the object so that it can get a number identifying itself. It's very important to have global IDs in this system because that's what allows us to actually go find a value anywhere it is quote-unquote allocated, as you've seen in the examples. So that's what we mean when we're sending a signal on this identity thing here. We're basically broadcasting our ID to whoever cares. And in fact, we're packaging that ID number up with a number indicating the type. 2 corresponds to a const cell. Every single object has an identity like this. Let's start up at the top where we actually have some user interaction. So up here we have a grab sensor and a controller sensor, which together detect when I am hovered over a const cell and pressing the X button. When those are both true, when it is this and this, then we send a signal to eval car, which basically goes to the const cell. And actually, let me select that wireless transmitter so that we can see it's actually a wireless receiver. This is basically sending a value inside this sphere, which corresponds, of course, to the thing in the car or value position. So this is telling whatever's there to evaluate yourself and report what you are. At the moment, this doesn't do anything interesting because the primitive plus here, the math primitive, handles eval right here. It receives eval, it loops right back around to basically report its own identity, and that's it. There's no fancy logic. It's simply getting that, returning it by 0 or 1 basically in order to prevent it from sending all the time, and then returning what it is. So eval on a primitive basically just says, I'm me, I'm a function, please go ahead. So after the const cell verifies this, it's like, oh good, you're a primitive. I'm going to tell you to apply now. That's another wireless transmitter in the same place. So now the primitive gets the signal to apply. And that's going to do a whole bunch of things. So before we leave the const cell, let's just look at what's going to happen when the apply comes back. That'll give us a good sense of what's happening. So basically, it evaluates the thing in the car position to see what it is. It tells it to apply, or basically to call as a function. This terminology is stolen from Lisp. And then, when it gets a result back from the transmitter on the other side, it's going to loop that back around to report to whatever was evaluating the const cell. I got lost in that sentence. Basically, if the const cell was told to evaluate itself, it will then evaluate and apply whatever's in its car position and then return whatever that returned. This is basically what allows us to sort of call sub-functions, where like we can have nested expressions in this system. So ultimately this all loops all the way back around. But let's dive into the math primitive here and start seeing what the bulk of the system really looks like. I mentioned these things are basically state machines, and you can tell because of this selector here. You remember that every time we tap on one of these like move to next output things, it'll just advance to the next state. And in fact, a thing that I forgot to demo, and will do so now, is that you can actually force it into whatever state you want. So instead of doing this next state thing, it will just forcibly go to state A or state B. Simply by sending a signal on a wire, you will force it into that state. Very useful for us because these state machines get kind of complex. So, this being the math primitive, every one of these state machines starts in an idle state. This is basically doing nothing. This is telling the math part of it to reset itself, and it is basically setting 0 in this little thing here called a memory cell, which I made, which is just like a number that it hangs onto. So this is the value that it will accumulate as it runs the expression. Now, remember that the const cell told it to apply. Well, that means that a signal is going to come in on this apply transmitter and kick us into state B. Now, when I was going through some of this before, it looks like state B is actually just kind of useless. I don't know what's going on. But suffice it to say that regardless of what that state is, the apply also comes over here. It splits apart the ID into a type, which just verifies like, hey, is this in fact a... what is this doing? Tell you what, I didn't rehearse this. The gist of it, skipping some of the intermediate details, is that it's going to get... Oh, right, I'm sorry. The value that it passes in on apply is actually the ID of the const cell that starts that node's arguments. So basically, what's coming in here is the ID that it should go to start walking. And so it basically gets that identity number, that ID number, which is the lower component here, and passes it off to the walker, and also sends a signal called walker go. So this is sending messages between state machines because the list walker is also a big freaking state machine. That go signal gets pulsed, it gets turned into a pulse, piped into this node, it sets the ID that it's going to go to, it runs this thing, which I won't bother explaining, to figure out where that thing is, it runs a bunch of stuff, including this follower thing, to actually go to that place, and then it kicks into the next state. Without getting into the gory details, because this is already a half hour long, it goes through a sequence of states related to walking, and this is basically like what you would see in just normal code, but of course it's super bulky here. So state A is the idle state, B is finding where the next thing is, C is going there, D is holding position and waiting to have an identity from it or something, E is actually evaluating stuff, and so on. So again, skipping the gory details, basically the plus here tells the walker to go to the start of the arguments and start walking. The walker, after it goes to the right place and gets an identity and knows what is in the car position, is going to send its evaler up there in order to see what it is. Now the evaler sends the eval signal. Now you'll remember that the eval signal is basically just give me a value that's usable in an expression. Now a number responds to the eval signal in the same way that the primitive does. It's like, oh, eval, that's me. I don't do anything fancy. I just report me, and you can come get a value from me. Well, the way that this started over in the const cell was also with an eval, or, by us pressing the button if we skipped it. But that eval will kick off a whole thing and it apply and eventually come back with a result for the evaler. So you can see how this sort of recursively can traverse these expressions that we've built up. So the evaler goes, gets a value, wires the result identity back to here, which goes into the next state. Now the list walker knows what node it should go to get a value, so it sends its value grabber off to get that. You've seen that little green thing run all the way over to this temporary stuff zone in order to pick up a number that was sort of recently allocated. And then the value grabber explicitly wires the value back to the list walker, and then the list walker wires the value back to the plus, which then adds it to its accumulator here, according to whatever math operation we're doing, and then tells the list walker, okay, I'm done using that number, you can move on to the next thing. The list walker then, in its final state, will decide, am I at the end of the list? If not, I go all the way back up to the start of this and start it again, or I finish up, I tell my evaler and value grabber that we're all done, you go back to your idle states, and tell the math primitive, I am done, you can begin reporting a value. What happens in this case is that we go into, I believe that's this D state, D for done, conveniently. What that does basically is that when all the walking is done and we have a value accumulated, this little chunk of code down here gets a position to spawn a number at and then spawns a number there. I won't go into the details, it's not really relevant. But then finally, after it's done doing all those signals, making the number, getting the identity of the number node that it just spawned, it sends that identity back to the const cell that created it, and it passes that value back along to wherever it was going. And if this were actually the latest version of the code, again, I screwed up the versions, this is where it would abort evaluation and be all happy. So that's the high level of the system. There is, of course, a ton of detail here. And if people are interested, I could just do a stream or something where I answer questions about it and try to continue extending it, but I think that this video has gone on long enough and it's basically time for me to try and wrap it up in some way. So this was a really interesting project for sure. Doing something like this really forced me to grapple with, like, what even is a Lisp? What is actually required? What makes Lisp Lispy? At the beginning I was thinking about parentheses and layout and thinking about how am I actually going to nest these expressions together? Do I need some kind of syntax parser? Can I just represent this more directly? I was pleased, for instance, to learn that you could just directly represent linked list data instead of having to do what a textual representation of Lisp does with parentheses and dots in order to parse to the same structure that we can just snap together here. That's an area where I think, despite gravity being wonky, I think that the Dreams approach is actually kind of intuitive and nice to deal with. But in addition, there were a bunch of questions like, what does it actually mean to evaluate something, to call a function, to return a result? I was wondering for a while if I needed any memory allocation, for example. I mean, would it be sufficient to just have a const cell kind of return a value over a wireless transmitter so that we didn't need to spawn another number in? Well, that doesn't actually work in the general case because of how Lisp can sort of return objects and pass them around. Like, imagine a function that returns a function. How am I supposed to have the const cell return a function over a wire? It needs to be another object that exists in the world. So there's all kinds of questions like that I had to grapple with as I was making this. And it's interesting that it seems the sort of fundamental Lispy, like the minimal Lisp thing is linked lists, functions of some kind, and of course these values. And it was interesting to see where the runtime, what does the runtime actually have to know about? And this is getting rambly, but the runtime basically has to know just enough about lists to traverse them and call functions, and that's pretty much it. Many other primitives like this would actually be much simpler than the math one. I didn't realize that when I set out, but I think that with a little bit of extra work, I could easily make something like a function that returns another function, and then the value grabber runs over and grabs that function, and then it gets called, and so on. I mean, the system's all there to do it, and it's all happening with just a couple different primitives, like a couple runtime features, and a couple what I would call messages. It was interesting to see that effectively there's only one or two messages that ever needed to be sent between things, and the rest was just sort of explicit sequencing that doesn't necessarily count the same way. We basically have eval to say, give me a value please, and apply to say, I know you're a function, please be called. And I'm sure you could implement other things like char and CDR and whatever that you would have in a normal list, but kind of that's the fundamental thing. So it was really interesting for me to discover how those features of a Lisp are equivalent to message passing in a small talky thing, or to sending messages over channels, or you can sort of see how many different ideas are bleeding through and getting not tangled up, but overlapping in this project. Anyway, it was very interesting. This is too rambly. I hope that this is interesting to you in some way. I had a lot of fun doing it, and maybe someday I'll find the time to continue extending this and make it do properly Lispy things. But that's all for now. Thank you so much for watching, and I will see you guys later.